Parts of similar triangles. Proportional perimeters theorem. If two triangles are similar, then the perimeters are proportional to the measures of the corresponding sides. So that's saying is that if the two triangles you're dealing with, your ratio, your scale factor, is double, that means that the perimeter from the first to the second would be double. So I'm going to take a look at the first example. This example deals with perimeters of triangles. So what I did for myself is I just labeled, this is the first one and the second triangle. So I'm going to say that X is what my perimeter of my second triangle should be. So I need to find first the scale factor. So I'm going to deal with the 24 and the 16 because YX corresponds to BA. The next thing I do is I'm going to set up a scale factor, 16 to 24, which is 2/3. So now I know that I just need to figure out what my perimeter of triangle ABC is. So what I did is I added up the three sides and got 48 plus 16 square roots of 5. I then replaced that over and placed it over the X. So I have 2/3 equals 48 plus 16 square roots of 5 over X. X representing the perimeters. Because if they have a scale factor of 2/3, that means their perimeters has a ratio of 2 to 3. After you cross multiply, I'm going to have 2x equals 48 plus 16 square roots of 5 times 3. So what I have to do is multiply the perimeter of the smaller triangle times 3 and then divide it all by 2. Once you do all that math, you'll get a perimeter of 72 plus 24 square roots of 5. And that's it for that problem. This is one of the reasons why I went over simplifying radicals and adding and subtracting them. On the bottom of the next thing that you guys have is just special segments of similar triangles. And we talked a lot about this in chapter 5, about altitudes, angle bisectors, and medians. So triangles have corresponding altitudes proportional to the corresponding sides, so they share the same ratio. Then you've got triangles have corresponding angle bisectors proportionally to corresponding sides, and then again with the medians. Right. So once you read through example 2, you can pause the video, and then when you come back I'll explain what the ratio is. Alright. Triangle ABC is similar to triangle MNO, and BC equals 1/3 of NO. Find the ratio of the length of an altitude of triangle ABC to the length of an altitude in MNO. Well, it's going to be 1/3 because of the fact that segment BC is equal to 1/3 of NO. So this is a 1 to 3 ratio. So because they have that ratio for the sides, the corresponding altitudes are also going to have the same ratio. Okay, a few more examples to go. So why don't you guys pause the video, take a look at the next few examples, and then when you come back, we'll go over them. Alright, so example number 3. In the figure below, so I just labeled the information that they gave me as I read along. It said that ED was an altitude. Okay, so outside that triangle, and JI is the altitude of the other triangle. Then they said that EF is 36, which is this side here. 56 is JK, and then ED, the altitude of the smaller triangle, is 18. So what I did is I set up a proportion. I went 36 over 56, so those sides of the triangle, is equal to the altitude over X. I cross-multiplied, got 36 equals 1008. Divided each side by 36 and got an altitude for triangle JLK of 28. Alright, next example. This one is interesting. So they give you a few pieces of information that you need to read through. So these are two different poles supported by wires. You have triangle ABC, which is the larger one, and that is overlapped by GED. So you've got this one and this one. Then they tell you that AF is equal to FC. So that means that AF is half of 80. So this is 40 and this is 40. Then they tell you that FG is congruent to GC, that is congruent to CD. So that means that this part of the triangle, F to C in the larger one, is equal to 40, meaning that GC, FG, and CD are all going to be 20. Okay, so we're going to use that to try to figure out what the height of the pole is. So we know that AC represents the base of the larger triangle, CG is the base of the smaller one. So you have an 80 to 20 scale factor. Okay. So that's double, so it's half. So if we know that, we can set it up as that if FB is equal to 2 of CE's, then we just need to plug in our 30 and for our FB, and then take half of it to get what the height of that pole is going to be. The only thing that's left to look at is the angle bisector theorem. An angle bisector in a triangle separates the opposite side into two segments that have the same ratios as the other two sides. So the angle bisector is still splitting it into the same ratio. So if you have a ratio of 1 to 2, you're still in a ratio of 1 to 2 when it separates that side. That concludes this section.